Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 32 and we will be looking primarily in this lecture the change in the threshold voltage at cryogenic temperatures. So, for those uninitiated in this domain, we will start with the basic definition of threshold voltage. We will also look into the various components which make up the threshold voltage. Then we will look into the threshold voltage at cryogenic temperature and especially the effect of threshold voltage in cryogenics due to bandgap widening, uniform interface trap charges and Gaussian interface trap charges. So, these two are primarily on traps actually. These primarily on the traps and this one is basically your EG widening which we have already studied. So, these three will be the case study which we will take up for understanding the threshold voltage sort of variation which we expect to see in the cryogenic electronics. Now, let us define threshold voltage. By the conventional definition of threshold voltage is that threshold voltage is defined as that gate to source voltage when the channel just near or just below silicon dioxide interface becomes as much n type as was initially p type. So, let us start with a basic understanding and let us suppose this is my substrate with p type, this is source drain, right, and then what I do, I put up a gate voltage here, I go on increasing it and once happens is that so initially it gets depleted and then it becomes inverted. The onset of inversion is when the electron starts to get accumulated near the interface and the holes are pushed back into the substrate, right. So, there is a depletion region here, right, there is a depletion region. If I am assuming that this is grounded, there is a depletion region. Now, the idea here is if you still go on increasing the value of gate voltage, say they were initially, because initially if you remember there are p type material, right. So, we have doped with the third group element, I have a p type material and let us suppose there were 100 holes available. Now, inversion will occur when 100 electrons are available per unit say volume or per unit areal volume, areal density is there. And that is the reason you see at this point, if you look at the second bullet point and the whole concentration at the threshold voltage, the whole concentration is exactly equal to the acceptor ion concentration and electron concentration is also equal to the value of the Na in the channel, which means that the charge neutrality is still maintained. It is further assumed that the mobility charge density is still negligible compared to the depletion charge density, right. So, the mobile charge carriers are very small as compared to depleted and the channel is considered to be long and still in equilibrium. So, there is a dynamic equilibrium and the channel is long. Channel is long implies that the electric field in the longitudinal direction is almost 0 or very small quantity. So, under these conditions the final expression of threshold voltage is given by this quantity here, right, where QIT is basically my interface trap charge density which also depends upon the value of the surface potential. I have a depletion charge density which also depends upon the surface potential. This is my metal semiconductor work function difference and this is my surface potential and this Cox is the oxide capacitance per unit area. So, Q by Cox is primarily the voltage which the external voltage source has to apply in order to deplete the channel and QIT upon Cox is basically the voltage from the external world which inversion trap charges has to be there. You see therefore, both are negative, you see these are negative here whereas this is positive and this is also positive quantity, which means as the surface potential becomes larger and larger, obviously you require a much larger gate voltage in order to invert the channel and therefore, the threshold voltage will be larger. The same is true for the metal semiconductor work function, but if your depletion charge is very large, you need to give a smaller amount of gate voltage in order to invert the channel and same is with that case of the interface trap charges. So, this is the general sort of components which are available to make the threshold voltage with you. This is basically the threshold voltage at cryogenic temperature. I wanted to showcase to you how the threshold voltage looks like at a cryogenic temperature. This is my valence shell or valence band and this is my conduction band if you look carefully. And the difference between them is approximately let us suppose 0.04 electron volt, the band gap. My EI is somewhere between EC plus EV by 2. So, it is somewhere in the middle of the conduction and the valence band, right. Now, if you insert a p-type material, you will get Na here but if the Na is partially ionized or fully ionized, this shifts from this region to from this to this region, and the difference is basically del phi f is the change in the Fermi level because of ionized impurities. This is for the p type, and on the left hand side is for the n type. So, when you have Na and when you have Na minus, right, you will have always the change in the Fermi level. Why I am showcasing you this is that if there is an incomplete ionization and you are left with certain charges available, then in that case it is much closer to the band structure as compared to those when it is not, right. And I am assuming here that n equals to Ni, intrinsic carrier concentration is maintained here. This is phi f from here to here. So, this is my phi f which I see somewhere from this edge to this edge is my phi f, from this edge to this edge is my Ei, Eg, right. And from here you can see that the intrinsic energy state is somewhere in the middle of Ec and Ev. Now, we have already learned about dopant freeze out. I will not go into details of this one, but when the hole density becomes equal to the acceptor ion concentration and the same density of electron is equal to acceptor, which means that if I do P into N, this will be nothing but Na square, because P equals to Na, N is also equals to Na, which means that the number of holes which are being contributed by the dopant species is equals to P, and I assume that the number of electrons are also to be same. However, at cryogenic temperature, because MOSFET channel actually starts at P equals to Na minus, because of dopant freeze out, not all the charged particles are able to contribute, and therefore Na minus is basically the fraction of the ionized dopant. So, if I say that Na minus is just 80% of the total fact, it primarily means that 20% of the dopant species have not been ionized. Now, initially the dopants are frozen out in the channel, and therefore, for bulk FETs the remain frozen deep in the bulk, which means that let us assume that the dopants are initially frozen in the channel. Frozen why? Because the temperature is very, very low, and therefore the dopants have not enough thermal energy to even vibrate or release any of the charged particle, and therefore deep down they are frozen below and they do not at all contribute to the electrical characteristics of the device. Therefore, the last point, if you look carefully, the channel has to be switched on or switched from P equals to Na minus to N equals to Na minus to region inversion. So, you see it is a p-type semiconductor, you require actually an electrons near the silicon dioxide interface. Now, it is so P equals to Na minus means the some contribution from the ionized impurities are there, but if you want that electron should also come out, you need to extract electron from the overall species, from the substrate, and then you will have an inversion to take place. So, it becomes doubly difficult for the threshold. So, threshold voltage changes drastically, because now it becomes doubly difficult to generate extra charge carriers at relatively low temperature. So, there are two cases as I already discussed with you. One is the complete, in fact there are three cases, but we will concentrate on these two to a larger extent. I have a complete ionization. In the second case, I have an incomplete ionization and my current is relatively low, and my third case in the next slide is an incomplete ionization, but I still have threshold voltage perfectly aligned with the requirement. Now, let us look at the complete ionization. All the acceptor ions have been ionized, and therefore, P equals to Na, and when you do a strong inversion, N will be equals to Na. So, these two are well defined, and I can explain to you very easily this concept. I am just replicating this figure from the previous discussion, and I say that I am assuming that the number of holes is exactly equals to the number of all acceptor ions, and number of electrons which you get is almost equals to Na. Now, when you do a band bending, if you remember, we say that the surface potential should be twice the Fermi potential. Why? Because in one Fermi potential it will be actually depleting, in the other Fermi potential change will actually make your surface potential go to the value equals to psi s, right. And that is the reason complete ionization is a picture which is well defined and well known. Let us look at incomplete ionization, where the threshold current is very, very low. Incomplete ionization refers to the fact that P equals to Na minus, not all have done, and at inversion therefore N must be equals to Na minus, because charge neutrality cannot be sacrificed. And therefore, psi s prime is the surface potential at incomplete ionization is actually equals to 2 times phi f star, where phi f star is actually the is this one. Please understand, phi f star is actually different from phi f. Phi f is till this much is phi f, right, in energy scale, and this is your phi f star. So, phi f star is relatively smaller as compared to phi f. Phi f is right from intrinsic till the edge of the fully ionized one, which is this one. This is the fully ionized one, right, and this is partially ionized. So, the Fermi level for the partially ionized is psi f star, and phi f is much larger as compared to phi f star. But the whole idea here is, since it is incomplete ionization, the current is so low that I will not be able to use any of the devices for practical purposes. So, let us come to case number 3. In case number 3, we require full inversion. Therefore, what we do is that we assume that the holes is not fully ionized. So, P equals to Na, but the inversion layer N is equals to Na, not Na minus, which means that the electrons from somehow or other I am able to extract that the electrons will be quite large in number, they will be band bending, and therefore, my psi s prime will be equals to 2 times phi f star plus del phi f, which is 2 times phi f star is from here to here, right, and then del phi f is this one which you are talking about. So, I will have perfect alignment of the potential. Now, if since you take 2 phi f plus delta phi f, you end up having a value of energy level which is very close to either conduction band and valence band. So, therefore, even if I have dopant freeze out, I still have a relatively larger amount of current available to me by virtue of the fact that these charge part or these energy states are very close to EC or EV, conduction band or valence band. Now, if you look at the metal semiconductor work function difference, so now we will look into individual. So, this was, if you remember, was the final expression which you see. Now, we will take individual one of them and try to break it down into various factors. So, phi m is equals to phi m minus phi s, where phi m is basically metal work function and phi s is the semiconductor work function. And therefore, I write down phi m minus this phi s can be written as minus chi minus phi f star minus Eg by 2q. Eg by 2q because half of it is basically intrinsic one, where Eg is the band gap and phi f star is the modified Fermi potential, which therefore accounts for the incomplete ionization in a sense. Now, let us look at the temperature effects. Now, we have modeled the threshold voltage, we have modeled the phi ms value, and we have modeled the other aspects. Now, let us go one by one and see the temperature effect. Now, we have already studied Varshini model, and it states to us that at low temperature the band gap widening takes place, and very low temperature there is a good substantial change in the Eg value or the band gap value. Now, unfortunately, we do not have a very accurate value of the increase in the band gap at very low temperature. Experimental values are not available, right, and therefore, it becomes difficult to predict what will be the value of EGT at very low temperature. Now, the increase in the band gap is actually offset by decrease in the value of chi, where chi is basically a temperature dependent electron affinity, right. Now, if let us suppose the band gap increases, but if the chi value decreases, these are two opposing phenomena and they generally tend to cancel out over a period of temperature range. Now, let us take up a practical example and show it to you, that if my Eg is 1.12 electron volt and chi, which is the electron affinity, is 4.05, then for all practical purposes we treat that phi m, which is basically the metal work function, is almost constant and independent of temperature. So, the only temperature dependent term in this factor is basically phi f star. This is basically a temperature dependent. This is temperature dependent, but we assume that the dependency is not very large. The dependency is most towards the phi f star. Okay. So, we write down now therefore that the Q depletion, which is a function of psi s star, is given as minus tau b times Cox into root psi s. So, there is a direct dependency of the depletion region charge concentration with respect to surface potential, effective surface potential, and this is known as the body factor tau b, and Cox is already known to you. So, what we have learned from this is that the total charge which is there in place because of a reduced temperature has got a square root dependency on the value of the surface potential. So, we have done with if you look back, go back to your this expression here, we are done with this, we are done with this, We are now looking into QIT, which is the interface trap charges because of room temperature. Okay, so let us look at the interface trap charges. The interface trap density QIT per unit area, right, per unit area is the areal charge QIT, is given by this expression, where DIT is basically the total interface trap density over energy range. So, if you have E energy and you have E plus delta E, within the delta E change, how much amount of total interface trap density are there, that is shown by DIT as a function of T. If you look at the right hand side, this is the variation of the interface trap charges with respect to energy, and it is almost Gaussian to a larger extent, and therefore, you can actually fix the value of EC and the W0, which is full width at half maxima, by doing certain changes in the type of doping when you do and the annealing which you do in interface trap charges. The maximum value is N0 upon sigma root pi. This D0 is basically the number of energy interface trap charges with respect to energy. So, you see most of the interface trap charges are somewhere around EC, and if you integrate properly, and as you move away and energy becomes very high or low, the effective amount of interface trap charges reduce. So, most of the interface trap charges are somewhere around 0 MeV at that particular point, very critically near that particular point. The interface trap charges are divided into two parts. We have an uniform trap charges and we have an exponentially increasing trap charge per unit area near the band edge. So, uniform charges are due to dangling bonds, right. So, if you have a dangling bonds means those bonds which are not satisfied, they are always dangling in the nature, there the charge density is always constant, right. There is a uniform charge density independent of space, whereas there is an exponentially increasing charge density near the band edges. Why? Because as you move near the band edges, because of defects, because of strain, the number of charge carriers exponentially increase near the band edges. That also contributes to the overall interface trap charges. So, the way we do it is that we generally express it in a Gaussian waveform. So, this was actually I had shown to you in the previous slide here, and it depends on the value of N0 and sigma, the total D0 as a function of E, right. Now, if you very simple, if E equals to EC, then e to the power, this becomes 0, and therefore, e to the power 0 equals to 1, and therefore, D0 at E equals to EC will be given as N0 divided by sigma root 2 pi, and that is what you are getting. You see at EC you are getting this N0 upon sigma root 2 pi you are getting, and as you further away from the EC value conduction band edge, obviously the occupancy falls down very sharply. Now, if you could have a Gaussian surface like this, I can have this, then this FWHM is very small, which means that even for a small change in the energy band, in the sense your interface trap charges drastically falls. So, most of it is located near EC, the EC value, right, the conduction band edge. Okay. So, we have discussed about these interface trap charges. 2 sigma is defined as my full width for this case, and for MOSFET only negatively charged acceptor traps in the top of the band gap are significant, right. This gives you QU, which is the uniform interface trap charges, as equals to minus Q times du psi f minus phi f star. Psi s is surface potential and phi f star is basically the modified Fermi potential, right, and du is basically the interface trap charges. As you therefore see, as the surface potential becomes very much different from the value of Qf star, my Qu uniform trap charges also tends to increase, right. For typical, the value of du is around 10 to the power 10 centimeter square per electron volt, and we are assuming that for all practical purposes uniform profiling has been done, right. So, I think we will stop here today because further requires a much detailed background. What we learned, let me just recapitulate in a maybe a 2 to 3 sentences. We learned what is the threshold voltage, how threshold voltage is related to temperature and charge. Within the charge, how is it related to the mobile charges and how is it related to the interface trap charges. The location of interface trap charges with respect to the conduction band is an important parameter, which also determines the value of the total charge, total mobile charge or uniform trap charge which is stationed in the system. Higher the value, lower will be the threshold voltage in a sense, right. So, this was the general scheme which we discussed in the previous half an hour. When we meet next time, we will finish this part initially and then we will go ahead with the other parts as well. I hope you enjoyed the talk. Thank you very much.